Our DeepDIVA project that we worked on the last month, it's an automatic synthesizer programmer. And maybe I start off a bit about explaining how a synthesizer programmer works. And some of my colleagues here in class, I must say I was a bit surprised, like they didn't have an idea what a synthesizer was. So I came up with this picture. This is a synthesizer, for example, kind of a complex one. Arun, can you show the other one here? This is also a synthesizer. Basically, it looks like a piano. Current and turns it into sound, okay? So the thing about a synthesizer is it's a very abstract instrument, so to say. You have a lot of knobs that basically transform the sound. A lot of different knobs, some of them have hundreds of knobs, so to say. So each set of knobs, each setting produces a unique sound, okay? So this is a background. And if you say you want to program a synthesizer, it basically means I find a certain sound using the knobs in a certain way. Okay, you can imagine that this thing is from the 70s. So nowadays, actually it's in replica. It's pretty new, but you can imagine that nowadays these things are also in software, right? So the DIVA, the name for our project, is coming from a software synthesizer. So it exclusively runs on computers. It has a GUI. If you watch the slide, this is how it looks. You can still see it has something to do with knobs. Yeah, it still has knobs. This particular synthesizer has about 400 parameters. And yeah, to program it can be a hassle. For a lot of people like me, it's fun. So I would never think about automating this. So why should I? The thing is just, if you think about companies that sell musical instruments and who's actually buying these things, nowadays more and more amateurs, so to say, are able, get the tools to be really able to produce their own music. There's a thing that happened in the last 20 years. To record your music, the microphones, the sound cards, all the instruments, they got really cheap. With computers now, you have your own studio at home. And so what happened is that these tools, they were used by professionals in the 80s or 70s, right? Who had a big budget. Nowadays, a lot of amateurs sit in front of these thousands of knobs and actually know nothing about it. But still, they want to use this, right? And the way you get around with this now is there's something like presets. So a preset is nothing like a super small text file that actually just remembers how you put the knobs in which position. So when you buy a synthesizer now, you get hundreds of presets. If they're not enough for you, you buy new presets. There's like $10, you get presets for horror movies, okay? And then you skip through the presets until you find one that you like. So this way you can program a synthesizer without knowing basically anything about it. But then again, there's some restriction to this approach, right? Imagine you have a certain idea of a sound and it's pretty, and you already know the sound because, for example, on one of your favorite songs, it's in that song. Or you have some recording of that sound. So the idea to automatically program the synthesizer here, in this case, is I would show the sound to some tool, and then this tool will output the preset that I can load into the synthesizer. So to say, our neural net knows how to twist the knobs of a certain synthesizer, in this case, the DIVA, and shows me how I can actually use this sound. So this is pretty straightforward now, describing our approach, right? If you have this, this thing here, we input a sound wave. We kind of transform this stuff. Maud is going to talk more about this. Okay, so, right, we have the sound wave, we input it in a net, and it outputs us not a sound. That would be an easy misunderstanding of the project, but it outputs a preset that is just a vector of a whole lot of numbers that make up the creation of a sound in a synthesizer. Okay, so how would we go about this? Of course, every good model can only be trained if you have good data. So how do you find data? In this case, you can actually make the data yourself because there are some tools. We found a particular one programmed by somebody. It's called HERDMAN. It's basically a tool you can use from Python that accesses your VST plugin, which in this case is our software synthesizer, and you can render sounds from Python. So what we can do, we make a loop and we just randomly generate presets, knob positions, so to say, and then generate audio for them. And we decided to do this for 2-second bits of audio. So now we just let it run through the night and let it generate 100,000 different knob positions, sets of knob positions, with their respective audio. And we kept all of this on our hard disk. So this was basically the dataset we were using. Later, if you have questions, we tried a lot of stuff. We tried to make massive datasets or smaller ones. So we ended up with this because it kind of gave us the best result. I think now Maud will explain a bit more how we actually transformed this data to put it into the neural net.
Thank you, Sebastian. So yeah, so basically now we ended up with a data set consisting of audio time series, but most deep learning models don't deal with audio in its raw form. So we actually, for our project, extracted 2 types of features from our data set. So audio is usually converted into an image by generating a spectrogram. And a spectrogram basically shows the amplitude against the frequency. So what we're looking at now is we're looking at sound in the frequency domain. But the thing is, we as humans don't actually hear frequency or the pitch linearly. So actually what we had to do is convert our spectrograms to a MEL spectrogram, which reflects more as how we humans hear the sound. And in a similar way, also, we as humans don't hear amplitude or the loudness of the sound linearly. So again, we had to further convert our spectrogram with a power to decibel scale so that the sound is really like how loud we hear it. So we ended up with MEL spectrograms that are a visual representation of the sound the way we as humans perceive it. So the brighter the color in the image, the more power a certain frequency has at that point in time. And then we also normalized our MEL spectrograms before we used it in our model training. All right. Then a second type of feature that we extracted, which is related, is also a time frequency representation of audio, or MEL frequency substrate coefficients. And these are a compressed representation of the spectrum of an audio signal. And these MFC coefficients contain information about the rate of change in the spectral bands. All right, so our aim was to train a model that could reconstruct the patch, aka the combination of synthesizer parameter settings that generates the original sound. Now, with extracting our features, we actually changed our audio problem into a computer vision problem. So we could actually use algorithms that also perform particularly well with images. But there's also a different way that we could look at features like the MEL frequency substrate coefficients, because you could also see them as a time sequence. Because audio information usually also follows a pattern. So we could also try out sequence models. And this is what we did in our project. We experimented with 2 different neural network architectures. So on the one hand, we tried out different convolutional neural network architectures that tend to work particularly well for images. And then we also used a bidirectional LSTM with highway layers. Now, the bidirectional part basically allows the model to access the complete sequence, both in forward and reverse order. And the highway layers provide a way for information to flow through the layers of the model uninhibited, and at the same time also through the kind of standard means to nodes with the activation functions. So apart from experimenting with these different neural network architectures, we also experimented with varying the amount of synthesizer parameters that were allowed to be randomized. So basically, we're varying the complexity of our problem and see also how that influenced the model performance. And then otherwise, we also experimented with training parallel models. So basically, we're grouping the synthesizer parameters according to their function, so in what way they influence the sound. And then we actually trained different models in parallel, predicting each of these different groups of parameter settings, so allowing these models to specialize. But at the end of the day, most of our models actually performed fairly similar, and we actually end up having to restrict the number of synthesizer parameters that were allowed to vary to actually have a reasonable model performance. But this is actually consistent with also another project out there in the literature that kind of tries to tackle a similar problem using a different synthesizer. So it just turns out to be a complicated problem. All right. So I'm just going to briefly discuss with you our model architecture of kind of the final model that we're presenting to you tonight. So we're using our MEL spectrograms as input into a convolutional neural network that consists of 4 convolutional layers intertwined with max pooling layers. And we have 2 dense layers and an output layer at the end. All right, so our model predicts a vector of numbers corresponding to the synthesizer parameters that generate the sound. And these are compared to the actual synthesizer parameters that were used to generate the input sound. And so when the true patch and the predicted patch are very similar, or the difference between them is very small, that is a good prediction. And we used as a loss function, we minimized the root mean squared error between the true patch and the predicted patch in our model. And also what you see here is kind of a visual representation of how our training loss and validation loss behaved across training. And as you can see, around the 75th epoch, we kind of started to overfit and discontinued, actually. But we were saving the model weights in between. So the model that we're actually using tonight is the one where the lines kind of cross over. All right. So we actually evaluated our model using different measures. So we looked at the mean absolute error between the true patch and the predicted patch. We looked at comparing the MEL spectrogram of the true sound versus the predicted sound and the difference between them. And of course, we actually listened and just compared the sounds. So what I'm going to do now is actually show you 3 different samples to give you a bit of an indication how well our model is performing. So what you can see here is the MEL spectrogram of the true sound, the true test sound. And Graham is now going to play how the actual true sound sounded. Put back on the sound. All right, so that is the true sound. Yeah. And what we're going to play to you now is the sound that was predicted by our model. All right. Those, well, I don't know how the quality of sound was online, but those are actually quite similar. And you can also see that when you compare the true and the predicted MEL spectrogram and the difference between them, actually the mean absolute error between the 2 MEL spectrograms is relatively low. All right, so we have another sample for you. Again, this is the MEL spectrogram of the true sound, and this is how it sounded. Beautiful synthesizer sound. All right, so that was the true sound, and now again we're going to play to you the sound that was predicted by our model. There we go. Okay, so again, not too bad, and as you can see, the 2 MEL spectrograms of the true and predicted sound look quite alike. But when evaluating our test samples, what we actually also found is that our model has some difficulties with certain sounds. So what I'm going to play to you next is, again, a true input sound, and then I'm going to show you how our model performed. So, yeah. Now, this is actually a little bit different, and that's also what you can see here in the true and predicted MEL spectrogram. And also in the mean absolute error, you can see there's a lot more error in there. But up to this point, I've showed you, or we evaluated our model based on test sounds that were generated by the DIVA synthesizer. And we're now going to go over to an actual live demonstration, and we're going to challenge our model, and we're going to input a sound coming from a different synthesizer, namely
input the file that was just sent to me. Live demo, nice. Very nice name. Okay, so here we can, so our model only takes in a 2-second clip. So what we have to do is tell it where to start the clip from. So I'm just going to start from the start, and then input a file name, live demo. That was great. Okay. And now when I click this, it's going to send it to the back end. It's going to run it through our whole model pipeline, create a prediction, and then hopefully send a preset back to us. Put this into our DIVA. So bear with me 1 second. Here we go. So here's our DIVA. And so we want to go to live demo. This is the configuration that our model actually predicted. So now what we're going to do is listen to the predicted sound. There we go. So that's what we were waiting for. Okay, so I'll just talk a little bit about the future of our product. So firstly, as you can see, we might need to improve the sound matching quality a little bit. Now, this is a constraint from a couple things. So firstly, we're only using about 11 parameters. So that means we can't really predict very complex sounds or anything like that, really. So we hope to improve that to the full array of parameters, which is about 281, I think. And secondly, the model also prefers some parameters to others. So we want to kind of even that out a little bit as well. So another really exciting avenue that we could go down is to test out something like a variational autoencoder, right? Quite hard to say. So how that would work is we would put a embedded layer of, we would embed the DIVA synthesizer in the decoder part. But there is a little bit of a caveat to this because the parameters that we receive from the DIVA aren't actually differentiable. So as we all know, we need differentiable weights in our neural nets. So that's a bit of a hard issue. But we are inspired by another project that is called DeepAFX. So it's trying to solve a bit of a different problem, but they have been able to solve this undifferentiable issue. So then moving on to the product, as Sebastian said, yeah, what we set out to do was to create a product where somebody could put in any synthesized sound, and then the arrangement would be on the dashboard of like the configuration. Currently, we can only put in about 2-second clips and just a single pitch. So I think in the end, we'll probably have a mixture of models, an ensemble, if you will. And that would probably then be better for varying lengths and varying pitches. And then finally, we'd really like more of an integration with the DIVA system. So as lovely as the web app is with all the cats and everything, it's probably not the easiest interface to use. So we really would like to make it more integrated with DIVA, maybe like a plugin or something like that, really. Okay, so that concludes our presentation. However, I think we probably want one last thank you to everyone. So a very big thank you to Tristan. I think you've been mentioned in every single one of these. You're an amazing man. So yeah, Tristan and everybody in the DSR family, all the participants, all the teachers, Jose, everybody. Thank you very much. This has been an amazing journey. We've had so much fun. Yeah, so thank you very much.